Hi everybody, this is Mrs. Michek, and we're going to be talking today about neutralization reactions. So before we get started, I want to talk to you about why we are talking about neutralization reactions. Ultimately, what this is going to lead us to is a titration where we use these neutralization reactions in order to figure out the concentration of either our acid or our base. So you will be given the concentration of your acid or your base, as well as the volume of your acid or your base, and then asked to find the concentration of the other one. So if you're given the concentration and volume of your acid, but only the volume of your base, you'll be asked to find the concentration of your base. But again, that's going to be for a titration. But this is going to be leading to that. You have to understand neutralization reactions and how to do those before we can even get into titrations. So what exactly is a neutralization reaction? You will notice the root word of neutralization is neutral. So we are taking an acid and a base, which are not neutral, and they are going to be reacting together in aqueous solution to form a salt and water. So they always form a salt and water. To remind you of what a salt is, so you might be going, does it always form NaCl? No, that's just table salt. So they're always going to form a salt. Well, a salt is an ionic compound. You might be going, oh yeah, what's that? All right, well, an ionic compound is made up of a metal and a non-metal. Okay, so we're going to be taking our acid, adding it to our base. They're going to be neutralizing and forming this salt, which is a metal and a non-metal, plus water. So let's take a look at our example down here. And I want to point out to you that these are going to be double replacement reactions. So to take you back to all of our different types of reactions back in that reaction unit, double replacement reactions are where we have the cations switching places. So our hydrogen and our sodium are going to switch places. So in this case, the hydrogen is going to now be combined with the hydroxide. So some people, when they actually do their switch, instead of writing water, they actually write HOH, and that's perfectly fine. The sodium is now going to be combined with chlorine. The way that we figured out that this was the correct chemical reaction, remember, we always use our charges. So sodium has a 1 plus charge, chlorine has a 1 minus. We do the switch, and we get NaCl. Hydrogen has a 1 plus charge, hydroxide has a 1 minus charge, and we get HOH. Or you can remember back to our definition of a neutralization reaction where it forms water, and you can know that, hydrogen and hydroxide are coming together. They're going to make that water. Okay. Now, you definitely need to, every time after you've figured out your products, you need to balance the reaction. So let's look and see if our reaction is balanced. We have 2 hydrogens, 1 chlorine, 1 sodium, and 1 oxygen and 1 oxygen. So our reaction is balanced, and we have 1 of each of our substances. That's going to be really important, again, when we get into titrations, because you're going to need to use the mole ratio. For this reaction, our mole ratio is 1:1 for everything, okay? But it will not always be 1:1. So you need to make sure that your reaction is balanced. All right, let's move on to another reaction. For each one of these, I told you above it what the acid and the base are. That's just for your knowledge, okay? So we have hydrofluoric acid plus lithium hydroxide. Remember, this is a double replacement reaction. So my hydrogen and my lithium are going to be switching places. Remember, they're going to the dance. Lithium and hydroxide go to the dance together. Hydrogen and fluorine go to the dance together. But who actually leaves the dance? Okay, so lithium is now going to be leaving the dance with fluorine. But we have to check their charges. Lithium, according to the periodic table, remember it's in group 1, has a 1 plus charge. Fluorine is in group 7, so it has a 1 minus charge. Do the switch, and we get LiF. Plus, hydrogen is now going to be combining with hydroxide. A couple ways you can look at this. If you remember, my hydrogen has a 1 plus charge according to the periodic table. Hydroxide has a 1 minus. That's one of those polyatomic ions that you needed to have memorized. Do the switch, and we'll get HOH. Or you can remember from our definition that we're going to get water. Okay? I'm going to go, and I'm going to keep it as HOH for our writing and for our balancing of the chemical equation. So we're going to make sure this guy is balanced real fast. All right. So I have hydrogen, lithium. Oops, I skipped fluorine. I like to go in order. Hydrogen, fluorine, lithium. And then I actually sometimes, when I'm balancing these, like to check in terms of my polyatomic ions. I didn't do that in the previous example. I'm going to start showing you that now. So this is a polyatomic ion, OH. Okay, and now I'm going to come over to the other side and I'm just going to copy so that I'm comparing each one the same. Hydrogen, fluorine, lithium, and hydroxide. All right, so hydrogens. Now when I count hydrogens, I want to count hydrogens by themselves, not ones that are included in the hydroxide ion. So I've got 1 fluorines, I've got 1 lithium, I've got 1, and hydroxide, I've got 1. Come over on my other side. Hydrogen that is not included in hydroxide. So with my HOH, my hydrogen right here is not included in the hydroxide. So that's 1 fluorine, 1 lithium, 1 hydroxide, 1. I've got 1 of everything. My reaction is already balanced. And again, remembering forward to when we do a titration problem, my mole ratio is going to be 1:1 for everything involved. All right, next problem. All right, for this problem, we've got sulfuric acid plus potassium hydroxide. So my sulfuric acid plus my potassium hydroxide, remembering again that we have a double replacement reaction. Oops, didn't mean to cross out that 2. Pink. And put that 2 back. Okay, so my potassium is now going to be combined in the products with my my sulfate ion. So this is where we need to remember back to what our polyatomic ion charges are. Potassium, according to the periodic table, has a 1 plus charge. Sulfate, if you don't remember, because it's been a while since we've looked at these, It is in your reference packet. Sulfate has a 2- charge. So in order to balance each other out, we're going to have K2SO4 plus, again, water. And again, sometimes I find it easier to make this HOH. How did that get there? I switched the hydrogen. The hydrogen is now combined with OH minus. Same thing as last time. We do our switch and I get HOH. If you want to write that as water, that's totally fine by me. I find it easier to write HOH when I go to balance. Okay, so for my balancing, I'm going to count everything up. How many hydrogens? And then look, I've got a polyatomic ion here. So I'm going to count sulfates. Potassium. And again, I've got another polyatomic ion. Hydroxide. Then I'm going to copy this onto the other side. Hydrogen, sulfate, potassium, hydroxide. How many hydrogens by themselves? 2. Sulfates by themselves, well, sulfates are always by themselves, or not by themselves, but how many sulfates? 1. Potassium on the left, 1, and hydroxide, 1. On the right-hand side, how many hydrogens not combined with a hydroxide? 1. Ooh. So we are not balanced right now. Sulfates, 1. Potassiums, 2. Oh, definitely not balanced. And hydroxides, 1. Okay, so we have 2 elements unbalanced. My potassium and my hydrogen. If you remember back to when we did balancing the first time, you might remember that it is easier to balance hydrogen and oxygen last. So we're going to balance our potassium first. In order to balance my potassium, I need to put a 2 over here. And I'm going to get rid of this arrow just so it's not confusing. So I'm going to put a 2 over here. That's going to change my potassium. I now have 2 potassiums, but I also have 2 hydroxides. So, changed my potassium, and that's good. But now I have 2 hydroxides and unbalanced that. Sad. Alright. I'm trying to balance either my hydroxide or my hydrogen. But, oh, look. They're together on this side. So if I put a 2 right here, I can kill 2 elements with 1 stone, or with 1 coefficient. Alright, so when I put my 2 right there, it gives me 2 hydrogens and 2 hydroxides. Why is this so important? Again, we're going to be doing titrations next week, and this ratio is very important. So keep that in mind, keep these in mind, and this should be helpful for your homework on neutralization reactions. And I hope you've enjoyed this.